Was it? Check grade school. Coach had told us. Yeah, wasn't one of his. I got 2 midterms, 2 papers, and a speech.
4 midterms.
Oh, God, yeah.
Damn, it's a lot. Busy.
Make it hard because like math, I'm kind of shaky, you know, so it kind of makes it hard to like study for it.
Right.
Yeah, not really, especially this, there's so much material in the first one. I'm just like sitting at the bottom, they got like differential equations, all of that, and then now 3-dimensional, all of that. Yeah.
Right. Okay, so let's do some review. Let's look at some differential equations. I'll try and talk up the things I think might be more likely to show up. Let's say we want to solve the following differential equation. Solve dy dx equal to e to the negative y times 5x to the 4th plus 5. Someone says solve a differential equation, you should be thinking it's going to be one of 2 things, separable or first order linear. This one is definitely not first order linear, because it's not linear in y. You have an e to the negative y, not linear. To be linear in y, you have to see a y to the first and a y prime and no other y. Now, I will say, I can come up with an exception to that, but generally that's what she. I'll show you an exception in a minute here. So this is not first order linear, so it's going to be separable. So we're going to separate. We're going to bring the y's to the left, the x's to the right. So I'm going to have, if I divide by e to the negative y, it feels kind of silly to write it like that, but we can write it like that. And then we're going to have a 5x to the 4th plus 5 times dx. And then integrate both sides, but I'm going to rewrite this as the integral of just e to the y. And this is the integral of 5x to the 4th plus 5 dx. Integrating e to the y, we get e to the y. Integrating the right-hand side, we get x to the 5th plus 5x plus c. And then solving for y, we get y equal to the natural log of x to the 5th plus 5x plus c. Not too terrible. Where did that example go? That was before. Let me grab one thing real quick here. This is one example I want to show you before I forget about it. Let's see here. Just gonna move these things out of the way. Sorry, one second. Also, I'll say I did on Canvas, I posted a bunch of practice exams and solutions from various professors. They might not be super duper, like all of it, maybe not be a great direct application to what you guys have done. Like some of them have like no graphing, some of them are like all differential equations, some of them have a lot more graphing stuff than you guys have talked about, but they're still worth your time and they do have solutions. And I would say skip the problems that don't feel like you need to practice them. And I think I actually have one more practice exam I can find that I think might be a pretty good fit. So I'm going to try and find that later on. Yeah, it's all everything you want to see is under modules. It's kind of, I think it's kind of near the bottom. It's like exam prep or something like that. All right, I can show you in a second. Sorry, one more. I just want to find this one problem I was looking at before. Oh my gosh, why are you being so problematic? There we go. Sure. So let's look at this example for just 1 second. We're not, well, we might actually do it. Yeah. Let's go ahead and look at, say, here's one. Let's say someone said to solve this next one, which is, where'd you go? X squared y times y prime minus y squared equal to 4. Now, if you looked at this from the very beginning, you might say, well, that's not first order linear because we have a y squared. While you're not wrong, not right exactly either, because if we manipulate this to get to the standard form, it might then look like a first order linear. Also, I don't think it's separable. Right? If you tried to get y prime by itself, you're going to get x squared y times y prime equal to 4 plus y squared. And then you're going to, you might be able to separate the, yeah, this one is separable. So sometimes you can do either thing, right? This one definitely you could separate. You could say x squared times y times dy dx equal to parentheses 4 plus y squared. You bring the 4 plus y squared down to the bottom. So you have y over 4 plus y squared times dy. And you can bring the 1 over x squared times dx over to the right hand side. You totally could separate this one, but I will point out you could also make it a first order linear. You could totally divide everything by x squared y and get y prime minus y squared over x squared y equal to 4 over x squared y. And then this would be y prime minus 1 over x squared times y. Oops, nope, I'm a liar. See how I'm a liar? Am I a liar? Yeah, I'm a liar. I'm totally a liar. I thought it was going to work out to be first order linear, but here's the lie. The right-hand side isn't a function of x. So it's good to check, right? Like if you're not sure, you can try other thing. I actually was going to start off by trying first order linear because I thought that was the one that was going to work, but it doesn't. Question right. Right, exactly. I should say it's not just a function of x. So I am unable to write this in the standard way for a first order linear differential equation. I can't write it as y prime plus p of x times y equal to just q of x because there's a y there. So that's why. Good to see, right? Definitely, if you're not sure, you can always go either way. Obviously, you can try either way. Most of the time, only one way is going to work. So if I was trying to solve this, I would be integrating both sides. For the left-hand side, it is going to be a u sub. We can see, I think without too much work, the integral of y over 4 plus y squared is going to be almost the natural log of 4 plus y squared. What am I missing? Where'd the y go? So I'm doing a u substitution, but I'm not actually showing my work. You here for 16C? Yes. Come on in. So if I took the derivative of the natural log of 4 plus y squared, what would I get? Well, I'd get 1 over 4 plus y squared, but then what would I have to multiply by? 2y. That's what the y is, but I'm missing the 2. So I need a 1/2 out here to account for that. We could have done the u sub, I'm just trying to save time on my exam. I could have said u is 4 plus y squared, du is 2y dy, so 1/2 du is equal to y dy. And then that integral is going to become the integral of 1/2 du over u, which is going to be 1/2 the natural log of u, which is then that. And on the right hand side, the antiderivative of x to the negative second is x to the negative first over -1 plus c. Right, that's x to the negative second, add 1, divide by the new power. And then we would solve for y. It's kind of a pain. We multiply both sides by 2, with the natural log of 4 plus y squared equal to, I'm going to write this as -1 over x. So really it's going to be -2 over x plus 2 times c is a constant. And then you exponentiate both sides. So 4 plus y squared equals e to the -2 over x plus c. And then y squared is equal to e to the -2 over x plus c minus 4. I should have made the change there, but I forgot to. I definitely should have changed e to the -2x plus c as y squared equals e to the -2 over x times e to the c minus 4, which really is going to be a times e to the -2 over x. And then that's all I can do, really. I can't do anything further because I don't have an initial condition. So the last thing I can do really is I can say y is plus or minus the square root of that, but I don't know if it's a positive or a negative because I don't have an initial condition. Again, right, so it depends on what they're asking for. Sometimes they will say solve for y, especially if they do give you an initial condition, but you also don't have, even if they ask for it, that doesn't mean you have to do all that, right? Use your time efficiently. I would probably, if I was on an exam, I might stop like right here and then go on to other stuff. And then if I had time to solve it more, go back. Let's look at one more. Where'd you go? Yeah. Let's look at, say, this next one. We have xy prime plus y equal to x to the 9,001st power times natural log of x, where initial condition is going to be x equals 1 and y equals 1. And to me, this is almost looking like a first order linear. Question, Josh. The general form? Yeah, the general form for the first order linear differential equation is going to be y prime all by itself plus some function of x times y to the first, y, equal to some other function of x. So to be able to apply the integrating factor to the first order linear differential equation, we have to first be able to write it in exactly this format. So to get from here to there, I'm going to divide everything by x, or whatever is the coefficient of y. If I divide everything by x, I'm going to get y prime plus y over x equal to x to the 9,001 times natural log of x divided by x. Now I should simplify this before I do anything else. I'm really going to write this as y prime plus 1 over x times y equal to x to the 9,000th power times the natural log of x. And now we do see it's in the first order linear differential equation format. So we're going to find our integrating factor, which is mu of x. Mu of x is going to be e to the integral of 1 over x dx. Integral of 1 over x is, we ignore the absolute value signs. It's just e to the natural log of x. And you definitely really want to do any simplifying you can here. So e to the natural log of x very nicely simplifies to just x. And then your teacher is totally cool with you just jumping into the solution, right? So then our solution is going to be y as a function of x is equal to 1 over our integrating factor times the integral of our integrating factor times our q of x function, which is x to the 9,000 times natural log of x. Which is not nice looking. So this integral here, the integral, if I multiply this out of x to the 9001 times natural log of x dx is not just something we can do straightforwardly. We have to apply what sort of method to integrate that. Yes, definitely integration by parts. So we're going to let u equal the natural log of x. And dv gets to be the rest, which is x to the 9001 times dx. My du is 1 over x dx. My v is x to the 9002 divided by 9002. And so then my integral is going to be u times v, the natural log of x times x to the 9002 over 9002 minus the integral of v du. So that's x to the 9002 over 9002 times 1 over x dx. What I'll point out about this last part here is that you essentially, when you simplify this, you get back to the same power you had before. This is going to end up equaling the natural log of x times the gross x to the 9002 over 9002 minus 1 over 9002 times the integral of x to the 9002 over x is just x to the 9001. And then we integrate that and we add 1 to the power and divide by the new power. So our answer is kind of gross, but we end up getting that y of x is equal to 1 over x times this whole integral, which is all of that. So it's going to be the natural log of x times x to the 9002 over 9002 minus 1 over 9002 times the integral of this, which is x to the 9002 over another 9002. And then finally plus c. Are we done? Are we ever done if I ask if we're done? No. Are we done? No, because we have to use the initial condition. We have to say that y equals 1 when x equals 1. So I know that if I set x equal to 1 and y equal to 1, I'm going to get what's c. So if x equals 1, I've got 1 equal to 1 times the natural log of 1 is 0 minus this is going to be 1 over 9002 squared plus c. So it looks like c has to equal 1 over 9002 squared. Not my favorite. No, not quite actually. Apologies. I have to add that over here. So c is actually going to equal 1 plus 1 over 9002 squared. Kind of gross. And then finally, you would plug that back in up here with your final answer. Of course, not enough room again. My final answer would be y as a function of x is 1 over x times the natural log of x times x to the 9002 over 9002 minus x to the 9002 over 9002 squared plus c, which we just found was 1 plus 1 over 9002 squared. Kind of some dumb numbers in this problem, but sometimes there's dumb numbers in your problem. Does that work? If we plug in 1, do we get 1? If I plug in 1, that's 1, that's 0, and that's 1 over 9002 squared plus 1. Oh, I'm off. Oh, no, that's a minus. Good. We're good. We're good. A minus 1 over that, that's a plus 1 over that. Those cancel and left with 1. So we're good to go. Questions? Other than why would someone give you such terrible numbers in a problem like this? I don't know. Someone would. Okay. I would encourage, I don't want to go over it because it'll take up all of our time, but I would encourage you to make yourself familiar with or practice the logistic differential equation. We've seen it so many times that I feel like it's very likely it's going to come up. Right. So I don't know for sure it's going to come up because I couldn't, but I will say it's worth practicing. So I'll just remind you, right? If you have the logistic differential equation, so like, let's say our carrying capacity is something like, I think it's like 500, then you're looking at something like dp dt is equal to k times p times 500 minus p. That's your differential equation. And then you have to solve it using partial fractions. So it's always going to end up being 1 over p times 500 minus p dp equal to k dt. The nice thing is if it's written this way, the partial fractions decomposition is super straightforward, right? This is going to end up being the integral of 1 over p plus 1 over 500 minus p. As I say that, I'm not 100% sure, so I guess I should check. So what I'm actually trying to say, right, is partial fractions. 1 over p times 500 minus p. I feel like I'm off by 1 over 500 somewhere. Is equal to 1 over p plus 1 over 500 minus p. Or 1 equals 500 minus p plus p. Right? I feel like, what am I missing? I'm missing something important. Not a negative. No, well, like right here, I did something kind of dumb that it's easy to miss. I forgot the a and the b because I felt like I already knew what it was going to be. This should be a times that plus b times that. And then if we set p equal to 0, we get 1 equal to a times 500. So a is 1/500th. And we set p equal to 500. We get 1 equal to a times 0 plus b times 500. So we get b equal to the same thing, 1/500th. So really there should be a 1/500. And then that's going to equal kt plus c. You multiply both sides by 500 and nothing changes really. Because my a, so really this should have been, that should have been a 1 over 500 right there and a 1 over 500 right there. And I factored them out to make life easier. Right. Because they happen to be the same. If I multiply both sides by 500, 500 times k1 is just k2, and 500 times c1 is just c2. I'm not really changing anything. And then we integrate, you get natural log of p minus natural log of 500 minus p. I guess I could throw in the absolute values, just be consistent, equals the integral of this, which is, oh, no, I already did the integral of that. Apologies. I don't need to write the integral again. I already did it. Don't write the integral again. Sorry, can you list here? And then this is where, so the integrating part, I think, is the easy part. It's the solving part that takes time. So, right, then you have to combine this together. All right, it's the natural log of p over 500 minus p equals, I'm just going to call this kt plus c. And then we e both sides. E to the kt times e to the c. I'm going to call a. And then you multiply both sides by that. Combine, like, I mean, you're fine. We're already almost there. Might as well finish. I know I said I'm not going to do it because it's going to take up too much time. Clearly not. So multiply both sides by 500 minus p. You get p equal to 500 minus p times a e to the kt. Distribute p equal to 500 a e to the kt minus p a e to the kt. Add that back over. So p plus p a e to the kt equals 500 a e to the kt. Finally, factor out the p and divide by the 1 plus a e to the kt. So you end up getting p equals 500 a e to the kt over 1 plus a e to the kt. And in general, it should turn out when you're solving this, there's like 3 different ways of writing people. Like I like this way because I can just remember, okay, great. My formula is always going to be p equals the carrying capacity times a e to the kt over 1 plus a e to the kt. Right. Where did the 1 over 500 go? Oh, from the first step here? Yeah, I multiply both sides by 500. Right. 500 times K1 is K2. 500 times C1 is C2. It's lazy, but it's what people do. So yeah, and then if you had initial conditions, you could use them to solve for A and for K. Okay. So certainly don't spend all your time practicing that because there's no guarantee it's going to show up, but it could show up. So don't ignore it either. All right. The last thing I'll say about differential equations is the kind of question I could also see him asking would be to say something like this. Yeah, I kind of like this version of it. I could either say something like show that y equal to e to the negative 3x plus 2e to the 3x plus c is a solution to, what do I got here? The differential equation. Wow, that's really hard to read. Y double prime? Yeah, sure. Y double prime minus 9y equal to 54. But more generally, a more interesting question from a teacher's perspective is to say, instead of show this as a solution, say, find the values of C so that this is a solution. It's a slightly more interesting question from a teacher's perspective, I think. So it is more likely to be asked. In either case, the process is the following. Take your solution. Take your solution. And then find whatever derivatives show up in your differential equation. So here I just need to find y double prime. So I'm going to do that. So let's see, I take the first derivative first. The y prime would be negative 3e to the negative 3x plus 6e to the 3x plus 0. And y double prime is going to be 9e to the negative 3x plus 18e to the 3x. I'm just going to plug in all the things I have into the thing it's supposed to be a solution to. So plug in y double prime and y to my y double prime minus 9y equal to 54. So plugging in y double prime, I'm just going to throw that in. Right. So I'm going to plug in y double prime equal to all of this for y double prime. I'm going to plug in y equal to all of that for y. So doing that, I get, let's see, 9e to the negative 3x plus 18e to the 3x minus 9 times e to the negative 3x plus 2e to the 3x plus c equal to 54. So now I'm going to figure out what will some of this distribute this out. We've got 9e to the negative 3x plus 18e to the 3x minus 9e to the negative 3x minus 18e to the 3x minus 9c equal to 54. These, cancel. I'm left with negative 9c equals 54, which means c had better be negative 6. That's the idea here, is that you're showing this as a solution and you're finding the value of c that makes it work. Specifically though, if someone says show this function y equals something is a solution to this other differential equation with y and y prime, y double prime, you need to find whatever derivatives in terms of the solution they gave you, and then just substitute those into the places that they go and see that it is equal to the other things it's equal to.
It's always going to show us as like y double prime.
Oh, I mean, not necessarily. I could have said something. I could have said something like, show very easily that y equal to e to the 3x is a solution to y prime minus 3y equal to 0. I was just saying, right? Whatever derivatives are in your differential equation, we need to find those based on what they're saying the solution is, and then substitute them in to show the solution. All right, let's move on from the differential equations. Talk about the graphing type stuff. Where'd you go? Yeah, sure. Yeah. Graphing stuff. Ugh. The problem with graphing stuff is really hard to kind of anticipate what someone might ask about. the thing, the thing I would probably say is the most likely to come up would be to find some sort of domain and range, and maybe be asked to graph, that's what I would ask if I was teaching. I don't know what he's gonna do. I'm just trying to say, this is what I think seems like a normalish question. So I might say something like, here's a function, f of x comma y equal to, do I really want to do that one? I don't love that one, but it's fine. Let's make it, sure. Equal to the square root of x squared plus y squared minus 16. Let's find the domain and range. Let's also talk about some traces and some level curves. Let's start with domain, because domain, at least we have a pretty straightforward process for finding it. For domain, got a square root, we just have to say, okay, that inside stuff has to be greater than or equal to 0. Which means x squared plus y squared is greater than or equal to 16. And I do recommend keeping x squared plus y squared together. Right, I know that x squared plus y squared equal to 16 is a circle, radius 4. So x squared plus y squared greater than or equal to 16 means we want everything on or outside of the circle of radius 4. There's my circle of radius 4. And I don't want any of the points that are inside of it, because like if I wanted 0, 0, 0 plus 0 isn't bigger than or equal to 16. So I don't want the insides. I want the entire outside of the circle. I should point out, this is the question, like graph the domain. If they just said find the domain, the answer I would write is that the domain is the set containing all points x and y such that x squared plus y squared is bigger than or equal to 16. There's really nothing else we can write for the domain. That's why it's a much more interesting question to ask you to graph the domain in the XY plane. That's what I would ask if I was writing the test. How about the range? If a range, you really have to look at your function and think about, or at least the real way I would do it is to look at and see how small can the function be? What's the smallest output we can get? Well, can it be negative? Can you pick x and y values that make this function negative? Definitely not. Square roots always give us non-negative results. Can it be 0? What could you plug in for x and y to make sure you got 0? 4 and 0. Yeah. So for example, 4, 0, 4, 0, 4, or negative 4, 0, right? Any of these points will give you f of x comma y equal to 0. That's the smallest it can be. How about the biggest? Right, you can get as big as you want. You just let x get larger and larger and larger and larger. The output's going to get larger and larger and larger. So our range here is 0 to infinity. Inclusive of 0, always exclusive of infinity. Graphically, what does this look like? Well, let's talk about some traces. So the traces. The traces on their own are not hard to think of what to do. So I'm trying to find like the trace in the, say, well, let's start with the XZ plane, for example. I'm just going to set y equal to 0. That is always how you're finding a trace in a particular plane. You're setting the missing variable equal to 0. So here, when I do that, sorry, you can't see my function anymore. When I do that, I'm going to take z equal to the square root of x squared plus y squared minus 16. And if I set y equal to 0, I'm going to get z equal to the square root of x squared minus 16. What does that look like? I don't know. I'm actually like really don't know. But I know where I can start. I can start at x equal to 4. Right, I have to start at x equal to 4. I can't start anywhere less than that. If x is 4, I get 0, and then as x gets bigger, z gets bigger. So if x is like 5, 25 minus 16 is 9. The square root of 9 is 3. I'm getting big fast. And it looks like this. Now, that's not all of it. Because x could be +4 or bigger, but x could also be -4 or smaller. Kind of looks like that. Sorry, it should look symmetric there. Apologies. Something of note is that often when you have this kind of x squared plus y squared deal, you're tracing the xz plane and you're tracing the yz plane, pretty much look the same. Right? If I look at the yz plane, then I'm setting x equal to 0, and I'm getting z equal to the square root of y squared minus 16. It's really the same thing, it's just using y instead of x. So graphing that, it's going to look the same. Here's my y-axis, here's my z-axis. 4 in either direction. I'm just getting bigger and bigger and bigger like that. I mean, the same up to my ability to draw it looking the same. And then finally, in the xy plane, well, we know what's happening in the xy plane. If we set z equal to 0, we're getting the square root of x squared plus y squared minus 16 equal to 0. Or in other words, x squared plus y squared equal to 16. Circle of radius 4. Now, if we want to talk about the level curves for a second, I guess I could draw this one, sorry. That was my circle. Level curves, you're just letting z be larger and larger and larger. So for example, if we pick z equal to 0, we exactly get the one we just talked about, x squared plus y squared equal to 16. If we pick z equal to 1 higher, we have the square root of x squared plus y squared minus 16 equal to 1. Or x squared plus y squared equal to 17. So you have a slightly larger circle when you go up 1. If we go up to z equal to 2, you get x squared plus y squared equal to 16 plus 4. You go up to z equal to 3. The 16 plus 9. So as we go up and up and up, we're just getting larger and larger circles. So if I was going to try and draw my level curves, it would look something like this. So when z equals 0, I get a circle of radius 4. That's when z equals 0. I'm just going to try and draw the next one that I know I can draw relatively, not terribly. When I go to z equals, say, 3, I get a circle of radius 5. Wow, that's good. So as we go higher up, the circles get bigger, which I think now, combining my traces with my level curves, I feel like I could probably try and do an okay job of graphing this 3D surface. It's probably going to look something like, well, I've got my traces there. So here's my YZ plane. So I'm just going to kind of draw that. 2, 3, 4. 4. It's going to be going up like that. Like that. And then instead of trying to like draw it in the XZ plane, that never works out for me. I would just say, think about what's happening with your level curve. So at 0, I'm getting just a circle. Radius 4. And then as they go up, I'm just getting circles that are higher and higher and higher. Sure. Yeah, totally. And so then if you want to kind of fill in the XZ plane part, you can say, oh, it's kind of going out like this. Or back like that. So a level curve is just if you were to cut this surface at a height other than 0, or even at 0. So like if I cut this at 0, I just get a circle of radius 4. Exactly. Level curves specifically are thinking about going higher or lower to get your what this two-dimensional thing looks like on that z equal to whatever plane. Often it's given to you. I will say the general practice is to say, I'm going to set z equal to c. And then say, okay, well, if I do that, I've got the square root of x squared plus y squared minus 16 equal to c. Square both sides. If you have an x squared plus y squared, try to isolate it, because we know we have something circular if that's the case. So I've got x squared plus y squared equal to 16 plus c squared. And I know, great, this is always going to be a circle, and the radius is going to be the square root of 16 plus c squared. So then you can say, tell me any C and I'll tell you what the circle is, right? C equals 0, my circle's radius 4. C equals 10, so I'm going up to a height of 10, my radius is the square root of 116. So people often do this to kind of make sure they're not calculating the same thing over and over. Right, they'll be like, draw the level curves for C equals like 1, 5, 10, and 15, for example. And then you would draw, but you draw the level curves on the two-dimensional plane, right? So like, let's say I wanted to also get in there, let's say I wanted to find level curves for like C equals 0, 3, 8, and 12, just for the heck of it. Then I would use this and say, okay, well, I know for C equals 0, my radius is 4. For C equals 3, my radius is 5. For C equals 8, my radius is going to be the square root of 16 plus 64, which is 80, which is almost 9, right? The square root of 80 is just a slightly less than 9. So, right, I have to go out like there's 4, there's 5, 6, 7, ooh, it's gonna get kind of big, 8, 9. So there's my level curve. Oh man, so that's a circle, pretend that's a circle. And then I shouldn't have picked 12, but I did. So for 12, right, our radius would be the square root of 144 plus 16, which is the square root of 160, which is a little bit less than 13. So the next one, which I'm not going to draw this, but that's the idea. You graph all those. Oh, and specifically though, you would label them. This is when C equals 0. This is when C, we usually say C and not Z. And this is when C equals 8. So you can see that as you get higher and higher and up, your circles get bigger and bigger and bigger. Right. Nope. We typically don't draw them on a 3D graph. You can, like I can totally draw, like I can say this is the level curve here when C equals 3, for example. But most of the time when someone says draw a level curve, they really mean to draw in a two-dimensional plane that is kind of like this is X, this is Y, and this is how high you are. Yeah. Usually when someone says level curves, they really mean draw it in a two-dimensional plane. All right, so I mean, one more time. Yeah, the quadric surfaces. So yeah, I don't know about as far as like what he might ask about that, but as far as identifying quadric surfaces, yeah, I would say look at the section in the book. So but really like we know that for quadric surfaces, there's 6 of them. And here's the very, very quick general breakdown. Z equal to X squared plus Y squared, paraboloid. Z squared equal to X squared plus Y squared, double cone. Or as you might think of this, X squared plus Y squared minus Z squared equal to 0. The reason I point this out is because then we start looking at the other ones, like say X squared plus Y squared plus Z squared equal to R squared. That's going to be a sphere. Or if you have different coefficients, an ellipsoid, right? You could have AX squared plus BX Y squared plus CZ squared equal to some number. It doesn't really matter what it is. That's going to be an ellipsoid. I think of these as being the same though. The sphere, ellipsoid is just kind of like a deformed sphere. You've elongated it in some way or scrunched it in some way. But the important piece of information to recognize here is that you have X squared plus Y squared plus Z squared equal to some number. And maybe they all have different constants, then it's an ellipsoid. Maybe they have the same constants, then it's a sphere. Okay. And then we have the hyperboloid of one sheet. So that is X squared plus Y squared minus Z squared equal to 1. Now, technically, you could have any one of them be the one that's minus. The one that's the odd man out is the axis that is symmetrical about. So since the minus sign there, we know we have symmetry around the Z-axis. But if it was say like negative X squared plus Y squared plus Z squared equal to positive 1, then you'd have symmetry around the x-axis. This one's gonna look like, so the other one's like, this one, looks like this. Paraboloid, double cone. Sphere ellipsoid, I'm not gonna draw. Symmetry, and then this hyperboloid of one sheet looks like you're going around the z-axis. Kind of like this, except you kind of deformed it out a little bit, so it's more like this. Sorry, it's not, my pictures are not excellent, but you can see it. But I want to point out there's kind of a, like, I kind of think of these together-ish. The difference here is that here it's equal to 0, so you get the origin. Here it's equal to 1, so you can't get the origin anymore. You have to kind of let either x or y be larger when z is 0 so that you get the graph shape. And then lastly, the sure. Negative x squared minus y squared plus z squared equal to 1. That's a hyperboloid of two sheets. This is a one sheeter. Up here, when you have one minus sign, this is a two sheeter when you have two minus signs. Still has symmetry around the z-axis because z is the odd man out. This one looks like, this one I'm not as good at drawing. Your hyperbolas look like they're going this way, but then you're revolving around the z-axis, so you've got kind of this kind of deal like that. It kind of looks like two like satellite dishes, kind of. That's the kind of way I think about it. What's that?
It's not connected.
They're not connected. That is why it's hyperboloid of two sheets. There are two sheets that do not touch each other. Yeah, good question, Josh.
So two sheets is symmetry around the one that stops.
Correct. So I would always say whether it's a one sheet or a two sheet, the one that is the sign that is different from the other two is the one that is the axis we have symmetry around. Or basically the axis you can think of like the shape being kind of rotated around. Like if I rotated the shape around the z-axis, it wouldn't look any different. Same thing here. Same thing here. The double cone, right? The double cone, the z is also the odd man out there. But the point of that really is that if you change the round of the equation, like if I said instead, x squared minus y squared plus z squared equals 0, well, then it'd be a double cone, but it'd be opening along the y-axis instead of along the z-axis. Similarly here, if this was say like x squared minus y squared minus z squared equal to 1, then it would be still a hyperboloid of two sheets, but the sheets would be, instead of opening up like this on the z-axis, they'd be opening towards you on and away from you on the x-axis. So that just tells you which axis things are kind of happening on. And then lastly, my favorite one, the oh my God, your book calls it the dumbest name I've ever heard of, which is a parabolic hyperboloid or something. I don't know. I would never call it that. Hyperboloid, whatever. It's a saddle. Call it a saddle. And it looks like a saddle. My favorite version is this one. Z equals y squared minus x squared. It's kind of similar to a paraboloid, except instead of getting two parabolas opening the same way, you get two parabolas opening opposite directions. One opens up, and then the other one you turn 90 degrees and opens down. So this one opens up like this in the YZ direction, and then in the XZ direction, it's kind of down like that. So then it kind of does this deal. And yeah, it looks vaguely. This is like the one thing I'm kind of not terrible at drawing, so I take every chance to draw that I can. Like, yeah, it's a pretty good picture. There's your saddle. And literally called a saddle because it looks like a saddle that you sit in, like a horse on a horse. Okay, so do with that what you will. I don't really know how much you can ask about this kind of stuff on an exam because it's just, I don't feel like they really ask you to draw these things because it's just not very conducive to being done on an exam. They might draw them for you and ask you to identify them, but again, I don't really know. I don't really know what your teacher's going to ask because he never gives any practice. Okay, let's do one last thing with our last 3 minutes here. Let's do one of these things here. Let's say, not that one. Let's do that one. Sure. Let's say for this function of xy equal to x squared plus 4xy plus 2y to the fourth. We want to find the critical points and then classify whether they're maxima, minima, or saddle points. And the first step to that is finding the first partials. We're going to take fx, that's going to be 2x plus 4y, and fy, which is, let's see, what is fy? It's going to be 4x minus 8y cubed. We're going to set each of those equal to 0. Now, sometimes this works out nicely. And you just be like, oh, I get x equal to 1 and y equal to 2. Not the case here. Here we have to do a little bit more, or put forward a little more effort to actually find our critical points. So if you don't get any obvious solutions, the next thing to do is to solve one of them, usually to solve the easier one, meaning the one that looks less complicated. I'm going to look at this one here. So what I mean by solve this one is isolate either x or y. So I'm going to, sure, I'm going to isolate x. I'm going to say that 2x equals negative 4y. So x equals negative 2y. And then I'm going to take that. I'm going to plug that in for x in my other equation. Plugging that in, I have 4 times negative 2y minus 8y cubed equal to 0. Wow, how'd I get a minus sign? Good question. I don't know how I got a minus sign there. I wasn't paying attention. Not less better. Okay, so then simplifying, I have negative 8y plus 8y cubed equal to 0. Great, I can solve this equation. Let's factor out an 8y. If I factor out an 8y, I'm left with a negative 1 plus y squared equal to 0. And it looks like I'm going to get 3 solutions. I'm going to get y equal to 0, or y equal to plus or minus 1. Now we're not done. We actually haven't found any critical points yet. All I found is half of 3 critical points. I found the y coordinate of my 3 other critical points. So now I'm going to take, welcome. It's all right. We're almost done. So then we're going to take our y values and plug them back in to our relationship here. So if y equals 0, we're going to get x equal to 0. If y equals 1, we're going to get x equal to negative 2. And if y equals negative 1, we're going to get x equal to positive 2. So our 3 critical points are 0, 0, negative 2, 1, and 2, negative 1. And then we have to plug those into the capital D thing. So capital D is fxx times fyy minus fxy squared. Fxx, we have to take the second partial with respect to x, that's going to be 2. Fyy, second partial with respect to y, is going to be 24y squared. And fxy, taking the partial of x and then taking the partial of that with respect to y, is going to be 4. I would say don't simplify this. It's usually not going to be beneficial to simplify it. It's usually much easier just to plug in your points to this thing unsimplified. Okay, maybe 4 squared, I'd write 16, but you get the idea. So when I plug in 0, 0, I end up getting 0 minus 16, which is negative, which means we have a saddle at 0, 0. Whenever D is negative, you get a saddle. End of story. Nothing else to do. When we plug in these other 2 points, so if I plug in 2, negative 1, I get 2 times 24 times negative 1 squared is 1 minus 16. And I don't really care what it's equal to. I just care that I can see that it's positive. 48 minus 16 is definitely positive. When it's positive, you have to check one more thing. You have to check either the fxx or fyy is whatever sign there. And they're both going to be the same sign. So here I can see that both fxx and fyy are positive. And if fxx is positive, that means it's concave up. So we have a minimum. And then lastly, we plug in negative 2, positive 1. We're going to get 2 times 24 times 1 squared minus 16 again, still positive. And my second partials are still both positive as well. So we get another minimum. We have a minimum at 2, negative 1, a minimum at negative 2, 1, and a saddle at 0, 0. What do you mean by, what do you mean exactly? Oh, like I could have found y equal to like -1/2 x and plug that in there. Oh, no, you can plug it into the other equation. So we were using this equation to get these solutions. And then after we got those, if we plug back in y equal to 0 here, now that you ask, I'm like, could you? Yeah, you probably could actually. Usually, but it's usually going to be easiest to plug it back into where you have that relationship right there. We should definitely wrap it up because it's 2:03. Good luck on your exam. I will post another practice exam that I think is probably the most possibly similar to what you're going to have. But yeah. What's that? Yep, I'll be heading over to CADS right now. I was planning on having class on Friday, but we don't have to. In fact, actually, you know what? I have a really good reason not to, because I need to, I'm driving up to Y-Recon on Friday, so maybe let's just plan on not having class on Friday. Yeah, I'll post that. I'll post that announcement. We will not have class on Friday. So, good call. I'm actually, I need to get going, but I am going to post them onto the Canvas and the Google Drive, which you definitely can have access to if you don't already. I don't. Are you on Canvas? So send me an email and say, hey, James, can you add me to Canvas? And I will definitely add you to Canvas. My email is jjparmenter@ucdavis.edu.
What was it? Sorry,
JJ PARMENTER.
At UC Davis.
That's correct. Sorry, Heather, I know, lagging here. Okay. I don't know if that's